Buckle up for this week's episode of C-Show News. Google made a time crystal that defies physics. Hey there, welcome to C-Show News. When we think of clocks, we think of objects that measure time, things like our watches or smartphones. We don't think of them as being able to control time. But that might not be true for much longer. A team of researchers from Google and elsewhere just created a synthetic time crystal that can make time run backwards, and they did it all with math. More specifically, with the help of a quantum computer named Sycamore. Sycamore is one of the first quantum computers that has shown some real promise at outperforming even the most powerful supercomputers that we have right now. It can do certain very specific tasks faster than any other computer. In 2019, Google said that Sycamore had achieved what they called quantum supremacy. This means that for this particular task, it would take a conventional supercomputer thousands of years to do the same thing that Sycamore did in about 200 minutes. That task was simulating the movement of 20 interacting qubits, the quantum version of bits that can exist in two states at once. And these qubits were set up in a way that allowed the team to test how well the quantum computer could simulate a process that follows the laws of quantum mechanics. They found that their simulation was dramatically more accurate than a classical supercomputer could ever be. Quantum computers are still very much in their infancy, but there is a lot of hype about their potential because the way that they process information allows them to bypass a lot of the limitations that we see in regular computers. They may be able to crack some of the world's hardest encryption codes, develop better drugs and materials, model complex systems that would take conventional computers thousands of years to simulate. There is a lot of stuff that we can only dream of doing with the computers that we have today. But before all of that happens, we may be able to use quantum computers to manipulate time itself. Not physically, though. The time crystal that this team created doesn't bend the rules of physics. It isn't some kind of exotic matter that warps space-time. Instead, it's a type of matter that exhibits a repeating pattern through time rather than space. If you look at a diamond, for example, it's a crystal lattice of carbon atoms. They're arranged in a repeating three-dimensional pattern. Now imagine, instead of looking at the arrangement of atoms from a static viewpoint, you watch the atoms over time. If the diamond is clear, you probably won't see much. But if you were watching a different material, say barium, hafnium, and oxygen, you might see something unexpected. The atoms would go through a series of repeated oscillations. They would start out in one configuration and then swap places in a predictable pattern. If you watched long enough, you'd see the same sequence of events again and again. That pattern repeating through time is what makes a time crystal a time crystal. And those repeating sequences of atomic movements are called a discrete time crystal. There are also continuous time crystals whose patterns change continuously with time instead of discrete steps. The thing is, no one had ever actually created a time crystal before. It was considered to be a hypothetical object that should exist based on equations and models. It was just never observed. So creating one is a pretty big deal. The catch here is that we didn't necessarily create one in the traditional sense. We didn't pull any exotic substances out of a periodic table or discover it deep in the earth or find a way to make it rain. What the Google team did was use their quantum computer to mathematically model a system of 5 qubits, then evolve the model through time. Like we said before, each qubit can exist in 2 possible states at once. The qubits in this model were entangled so that the state of one qubit depends on the state of the others. At the beginning of the experiment, the qubits were set up in a specific way. After running the math for a little bit, the researchers saw the qubits start to arrange themselves into a repeating pattern, swapping places and returning to the initial configuration over and over. It was on a physical time crystal that would have been created under extreme heat and pressure deep within the Earth. It was a mathematical representation of a system that appeared to have the properties of a time crystal. This brings us to another catch. A big part of the reason why this is such a momentous discovery is that these guys are physicists. They're computer scientists. The math they use to create this so-called time crystal is normally used in the field of condensed matter physics. But the group needed to make sure that they were actually dealing with a time crystal and not some other kind of quasi-particle. So they sent their results to several groups of physicists who agreed that yes, this was indeed a time crystal, making it the first ever created. Now, this whole thing started back in 2012 when the Nobel Prize-winning physicist Frank Wilczek first proposed the idea of a time crystal. He suggested that an object that oscillates between two configurations could theoretically exchange energy with its environment and still return to its starting point indefinitely. Normally, when an object moves from one configuration to another, energy is required. For example, pulling a rubber band gives the rubber molecules kinetic energy. But if the object can return to its initial state without getting that energy back, then it appears as though time is running backwards. Of course, this isn't truly reversing entropy, the overall tendency of things to become more disordered. The time crystal simply returns to its initial configuration without increasing the entropy of the universe. It's a little weird, but that's the nature of quantum mechanics. You might be wondering why we read talking about this so much when it's basically just a bunch of math. Well, let's be real. Physics is getting weirder, and sometimes it's hard to keep track of what's going on. Luckily, you don't have to get a PhD in quantum mechanics to understand what's happening. You can stay right here every week as we break down the latest discoveries in physics and explain what they mean for the future of humanity. All that said, it's really exciting to see a new phase of matter for a couple of reasons. First of all, we haven't discovered that many phases of matter to begin with. Technically, there are 6, but we're familiar with only 3. Most of us learn about solids, liquids, and gases. Plasma, which is often referred to as the 4th state of matter, isn't technically its own phase. It's just a gas with an extra amount of energy. Bose-Einstein condensates and fermionic condensates are the last 2 phases that require incredibly low temperatures to exist. But time crystals could lead us to discover even more phases of matter. Some researchers suggest that a time crystal could exist in a lab at room temperature. If that's true, it could be the first new phase of matter that we've seen since 1998. Discovering a new phase of matter is a big deal because it means that matter has some other property that we were unaware of before. Take magnets, for example. They exhibit ferromagnetism, which is a unique property that comes from their atomic structure. Ferromagnetic materials form magnetic domains. These are regions where the magnetic fields of adjacent atoms align with each other. Domains form because unpaired electrons spin in different directions and influence nearby electrons. The trick is to find materials whose magnetic domains stay aligned at room temperature. When that happens, we call the material a ferromagnet. Of course, not all ferromagnets are the same. Some are better at conducting electricity, others are stronger at keeping their domains aligned. It's all about finding new combinations of elements and structures that result in a material with the properties that we want. And we're doing the same thing with time crystals. The Google team's time crystal lasted for around 30 seconds. But other researchers think that we could make them last much longer by changing the composition of the material that they remade of. And that will open the door to understanding its properties and how we can use them. Time crystals have a lot of potential applications, especially in quantum computing. Time crystals can exhibit what's called topological order. Topological order describes how quantum information is stored in the relationships between particles rather than their specific locations. It's similar to how the surface of a donut has topological order. No matter how much you stretch or twist it, a donut is always a donut. As long as the number of holes remains the same, you can't turn it into a pretzel. That's because the holes, or voids, preserve their connectivity. It's the same with topological order in quantum computing. If you try to copy a block of information, then move it somewhere else, some other block of information gets destroyed in the process. But because of the topological order, nothing is lost. That could be useful in building fault-tolerant quantum computers. It's early days, but we'll be watching to see how this research develops. And you know what else we'll be watching? Our community grows every day thanks to all of you. And you can join in the fun too. Head over to our support page to get involved. Don't forget to subscribe so you're notified every week when we release a new episode. And as always, thank you for watching.